If you've taken an introductory statistics course, if you remember nothing else from statistics, you likely and really should have heard the phrase, correlation does not imply causation. But it turns out that with some additional restrictions, in some situations you can actually establish a causal relationship between y and x. Hello, welcome back to the Quant Plus YouTube channel. Today I wanted to bring to your attention a few common techniques for establishing a causal relationship through a statistical model. As we alluded to at the introduction of this video, often the idea of correlation not implying causation is really drilled into the heads of students in introductory statistics classes. And while this is true, it doesn't really address the entire scenario, right? It doesn't really establish the full picture. And especially in social sciences such as economics, political science, and other related fields, establishing causal relationships is very important, but at the same time it is not feasible to perform experiments, right, on large scales, whether because the scale of the question is far too large to conduct a controlled experiment, or whether it's just unethical to do such a thing. And so in those scenarios, there are some established techniques for using the observed data and still trying to establish some degree of causality. And I've listed out some common techniques used when trying to establish causality or performing causal inference. So the four techniques that I'll touch on today are instrumental variables, difference and differences, regression discontinuity, and fixed effects. I also wanted to bring up the idea that the terminology and examples I'm using are primarily coming from economics and econometrics because that's the field in which I have more experience. There are similar ideas in statistics, purely statistics, as well as in biostatistics, political science, and so on. Also in medical applications. So to begin with, let's discuss instrumental variables. If we think about our standard linear regression model here, an instrumental variable comes into play when we know that we have an omitted variable, and because we have an omitted variable, we know that our coefficient estimates, right, our beta values, are incorrect, right? Whether we know that they're underestimates or overestimates, we know that they're not correct, and because we know that those beta estimates are incorrect, I should say, we know that the model that we have here is not placing the accurate effect of each explanatory variable on our variable that we want to predict or analyze, and so we can't really establish causality, right? Because when we're establishing causality, our main goal is to account for all the things that can be directly affecting y, the variable that we want to analyze, and to account for each of those things accurately. So in such a scenario, one technique that you can use is the use of an instrumental variable, where in short, whatever instrumental variable you're using, you want it to be correlated to one of the x's that is hard to measure and therefore likely omitted from your model, but not directly correlated to, or not very correlated to, your y variable, the one that you want to predict. And so as an example, let's think about trying to determine the effects of smoking cigarettes on general health. And sure, there have been numerous studies over the years that show a correlation between smoking cigarettes and poor health, but to be able to directly say that smoking caused such and such an impact on health, we have to account for things like the overall health of the person, other conditions potentially, such as maybe depression, diabetes, high blood pressure, and numerous other potential issues. And so if you were to trying to model that scenario where the variable that you're trying to predict, so your y variable is health outcomes, and one of your x variables is smoking, you might want to use cigarette taxes as an instrumental variable, right? Because a cigarette tax, there should not be there the levels of cigarette taxes in whatever locality that you're in should not have a direct impact on someone's health. But we would also assume that in places where cigarette taxes are high and cigarettes are therefore less affordable, there's a higher barrier to entry to smoke, and it's really something that would allow us to account, to say if there is some kind of correlation between health outcomes and cigarette taxes. Well, cigarette taxes, as we said earlier, should not be correlated with directly with health outcomes. But if there are, then that could be evidence of increased smoking having adverse health outcomes, because by having more cigarette taxes, if people are still paying them, that means that people are smoking. But there also cigarette taxes should also not be impacted necessarily by other potential health issues such as diabetes or high blood pressure, and therefore you can more direct or more accurately measure the effects of adverse health outcomes and smoking. Moving on to another commonly used technique, that's going to be difference in differences. In a nutshell, what we want to do is that we want to be able to directly compare two data sets that are nearly identical in every way except for a particular outcome variable that we want to consider. So one quite well-known example of this was that in the early 90s, if I remember correctly, New Jersey had increased their minimum wage by some amount, and the neighboring state of Pennsylvania did not. And well, this presented an opportunity to test one of the commonly held ideas in the economics literature, which pretty much says that minimum wage laws are a price floor, and accordingly, because they are a price floor, by implementing minimum wage laws, that should cause unemployment. And so in this particular example, they were able to look at people very close to the New Jersey-Pennsylvania border. And what they saw was that these two groups of people were essentially identical in every way that you would expect to have an effect on income, right? So things like demographic information such as ethnic background, education, prior working experience, ethnicity, work industries, all those potential factors that you'd typically consider when you're trying to predict someone's wage or income were very comparable across the two groups. And because they were very comparable in the two groups, you could say that any differences that you saw in the levels of unemployment were directly as a result of the change in the minimum wage laws. Not that it's particularly relevant to explaining the idea of differences and differences, but if I remember correctly, that particular study found that while there were some negligible differences in employment, they weren't statistically significant and did not lead, and that study did not support the commonly held idea of unemployment as a result of minimum wage laws. Another common technique, and the next one I'll touch upon, is regression discontinuity. So, kind of in a similar vein to differences and difference, or difference and differences, I always have it backwards. When there are strict cutoffs for things, or strict and arbitrary cutoffs for things, then that really presents itself as an opportunity to test different ideas. And in terms of a model, how you would see it play out as is, let's say you're trying to predict your y variable, whatever it may be, and you have your different x values, right, your different explanatory variables. Your regression discontinuity would play out as a dummy variable, which I put in as d right here, pretty much distinguishing whether you're below some cutoff or above said cutoff. And the value in this particular model of beta 2 is the direct effect attributable to whatever outcome is associated to that particular cutoff. Now, to give a particular example, suppose that there is some kind of poverty alleviation program, and the way the program is structured is that if you or your household has an income below whatever cutoff, let's say for the sake of argument $30,000 a year, then you qualify for some kind of program, let's just say some kind of supplemental income program where the local government or the government in general would provide you some kind of payment, whatever the amount may be. And so one idea some people have put forth, and something that can be tested in such a scenario, is that it's possible that for people who are close to that particular cutoff, but just above that cutoff. So in our particular scenario, let's say that an individual is making $31,000 a year, where $31,000 a year is just above that cutoff of $30,000 a year, and they would not qualify for that supplemental income program. Then one idea that has been put forth is that individuals in such a situation are disincentivized to work because it's to their benefit to lose whatever income from not working, because once they fall below that particular cutoff, they then qualify for this program. And so how you can test such a theory is that you would compile a data set. Let's say that you're trying to predict unemployment levels, so unemployment would be your y variable, and things that you might consider as explanatory variables for unemployment in an individual, so maybe things like military service, established health issues, education, possible criminal background, years of experience, ethnicity, gender, etc. All those things would be included in your x variable, but you'd also have this dummy variable, which I labeled d. And what that dummy variable is purely a yes or no variable, right? So a 0 or 1 variable, where 0 indicates that this individual, let's just say, is below the cutoff, and a variable of 1 indicates that they're above the cutoff. And so if we look at individuals who are just below the cutoff and just above the cutoff, any difference in their employment numbers would play out in terms of the value of the beta 2 coefficient. And that beta 2 coefficient would then be a measure of how much people are or are not disincentivized from working if such a program would be implemented. And the last general technique I wanted to cover, fixed effects. Right? So the theory on fixed effects definitely goes far beyond what I'm putting forth here, but in a nutshell, what you want to think about is including dummy variables, right? So variables that are either true or false, and if you come from more of a background in math, you can think about like a Boolean variable, right? Being 1 or 0, true or false, etc. And these are accounting for different categorical information in your model. So again, touching upon the idea of income, let's say that you're trying to predict income and some of the categorical variables that you're considering are gender, ethnicity, and military service. All of those variables are categorical in the sense that there isn't an inherent ordering to them, right? There's no inherent ordering and there's no inherent numerical value associated to each of them. But those are still things that you want to consider, right? Because we would expect income levels for those in good health to be different from those who have some kind of long-standing disability, as an example. And so you'd want to include those things as dummy variables where, let's just say the first dummy variable would be 1 if a person just has a disability and 0 otherwise. And then by looking at the coefficients of the corresponding coefficients, so let's just use an example and say that D1I is a dummy variable indicating whether someone has a disability, then the value of the beta 2 coefficient would measure the expected effect on employment of that condition. Now, the reason we're calling this fixed effects is because we would expect the effect of unemployment on income level to be pretty consistent across all individuals. And it's much, and the way I think about it is that it ties back to the idea that when you're establishing causality, you have to include all the things that can have a direct effect on your y. Right? You don't want to include things that do not have a direct effect. You do not want to omit any things that have a direct effect, because both of those will have the effect of having inaccurate values for your betas, and therefore if your betas are wrong, that can't be a causal inference because you're not assigning the correct impact of each thing. Now, the last topic I wanted to bring up, although it's not necessarily a technique, quote unquote, it's something that you want to consider when you're trying to establish these type of models. And those are the idea of multicollinearity and heteroscedasticity. So multicollinearity, you can think about it as there being some kind of covariance between your xi's, right? So your xi's are your explanatory variables, and if there's some kind of covariance between them, then you know that very likely that your coefficients are inaccurate because you don't know if you're accounting for the effect of one variable, one particular x, or another particular x, or some combination of the two. And we'll come back to an example of that in 1 second. The other idea I want to bring up is heteroscedasticity, and that's pretty much the variance being non-constant. So in terms of a visual interpretation, if we look at the drawing on the left, the sketch on the left, where we have homoscedastic scenario, where you can see that if we think about the green dots as being our data points, they are all a fairly consistent distance away from our blue line, which is representative of our model in this case. And if we look on the right, that's a case where we have heteroscedasticity, and you can see that for x values around here, the variance or the distance from our model is significantly larger than at either extreme, right? So down here or up here. And well, to bring up an example, so multicollinearity. If we're thinking about a model in which we're trying to predict, let's just say, fuel consumption in a vehicle, you might consider both the engine size and the number of cylinders as factors that would impact fuel consumption. If we're dealing with a standard internal combustion engine, you're using gas, etc. Well, the issue here is that most cars that have a large engine, let's just say by volume, also have a large number of cylinders. And many cars that have a smaller engine, let's just say by volume, also have a smaller number of cylinders. So you can think about it as the large pickup truck with a V8 and has a huge engine versus the little Honda Fit that has, I believe, a 4-cylinder engine, and it's quite small. And the issue there is that if you're trying to establish such a model where you're trying to predict fuel consumption according to these different variables, how can you tell the effect of engine size apart from the effect of numbers of cylinders? And not to mention that there's some kind of covariance, right? So some kind of combined effect of those two variables. How can you possibly account accurately for all of those scenarios? So instead, what you typically do is you'd include only one, engine size or number of cylinders, and you might include some kind of instrumental variable to account for the other. As for the heteroscedasticity aspect of things, there are several ways that you can account for this, and it doesn't generally have the impact of creating biased estimators. And by biased estimators, on average, your coefficients in your model in terms of, let's just say, the value of beta 0, the value of beta 1, and so on, those are generally accurate. But because your variance values and your standard deviation and standard error values associated to those different coefficients are no longer correct, things like hypothesis testing often will give you incorrect results, right? Because if your variance is understated, and reality your variance should be larger, then things that appears to be statistically significant, because they appear far from the mean, are in reality not statistically significant, because the measure that you're using for establishing significance and your yardstick essentially is incorrect. That is maybe a little bit of a secondary concern, and there are a lot of techniques that you can use to account for that, such as using a generalized linear model where you apply different weights or different importance to different observations, or like a heteroscedasticity and autocorrelation corrected standard error. There are different techniques that you can use for correcting for these issues. If you found this content informative, I would appreciate your support. Thank you to those of you who have already been supporting the channel. And if you found this content informative, again, please like the video, share it with your friends and family, and subscribe to the channel. And if you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great day.